This is the third of our measures. What was the first measure we did? Very good. What kind of tendencies? Very good. Measures of central tendency. Mean, median, mode, and variance. Mean, median, and mode. Then we went to where? Measure of what? Very good. Variation. How is your data centered about that? And that was your variance and your deviation. Now we're going to talk about the ones that you're most familiar with. Before you went to college, how many of y'all took the SAT or the ACT? You're waiting for your score. The score you got when you looked at it wasn't really what it meant. It wasn't actually the raw score. So if you made a 1200, that doesn't mean that you did really well or did really poorly. It's relative to how everybody else did. Because then you have to go through a calculation that describes how, according to your test score, how did you do to everybody else? Because then you have what's called a percentile. And we'll talk about that in a second. So the third method we're going to talk about is the measure of position. This is where your individual score sits as opposed to everybody else's. The first one we're going to talk about is called the standard score. Another name is the Z-score. The standard score tells us how many deviations are you from the mean, like we just talked about. So how many standard deviations a certain score is from the mean. The formula we're going to use for the Z-score, it's a Z-score. Later on in chapter 6, you're going to see when we do these, we're going to be using these scores to tell us how many percent of the data falls below that. So the formula for a Z-score is the actual value that you have, your score, minus the mean. So it's X minus X bar over the standard deviation. So the Z-score, X minus X bar over S. Can it be negative? Yeah, because your actual score could be less than the mean. So it's to the left, which means the mean's bigger than yours, so it's negative. Could it be positive? Yes, so the opposite reasoning. Can it be zero? Can your Z equal zero? That's what you're gonna say, wasn't it? I hope. If your score is the same as the mean score, or you scored exactly what the average of everybody else scores. If that's the case, X minus X bar equals what? 0, so the z-score is 0. And we're going to learn a lot that after everything's said and done with this z transformation, the mean goes here, it's the center, and it becomes a z-score. So this could be any number, but the z-score is 0. When we transform these things to relative to z-scores, the mean, I think, if x equals the mean, then it's 0. So that means anything to the right is positive, anything to the left is negative, relative to the z values, standard deviations you are from the mean. So let's look at the first example. A student scored 65 on a calculus test. That had a mean of 50 and a standard deviation of 10. The student also scored a 30 on a history exam with a mean of 25 and standard deviation of 5. Compare the two tests. You have that on your packet. Oh yeah, you have to go. Have a great weekend. I'm working on it, yes. So yeah, so please send me, if I have to, I'll resend a whole new sheet with new links. No, I'm sorry, it doesn't work. It should have worked. There's no reason it should have stopped working. But thank you for telling me that. All right. So let's compare the two. So we have our calculus exam. What do we have here? We have our mean of 65 and a deviation, mean of 50, mean deviation of 10. This is for calculus. And for history, the mean was 25 and standard deviation was 5. The student score was a 65 in calculus and a 30 in there. So since we're comparing these two, again, we're comparing apples to oranges. Why are they not the same type of scores? Why can't we just say compare them straight up? Well, no, the tests themselves are different. Or was the history one, did it have more fill in the blanks or matching as opposed to the calculus? You have to work it out yourself. So they're not the same type. Do they have the same number of questions? Do they have the same type of questions, the difficulty level? So all this sort of stuff. So remember, the formula we have to use is x minus x bar over s. So 65 minus 50 over 10, 30 minus 25 over 5. So 65 minus 15 is 15 divided by 10. Because whenever you divide by 10, it's just move the decimal place one to the left. So the z-score for the first one is 1.5. And the z-score for the second one, 30 minus 25 is 5 divided by 5 is so what do we know? All we can do here is discuss the relative position of the student. So the relative position of the student is the calculus had more variation, more deviation than the history score did. We can't say anything else. Later on in chapter 6, we can see exactly how many students is this person smarter than, the score higher than, what percent. It's all in a table. Actually, for this one's pretty easy. Since it's one standard, what this says is this person's score is 1.5 standard deviations to the right of the mean. That's what that score tells us. It's 1.5 standard deviations to the right. This one says what? It's 1.0 standard deviations to the right of the mean. Little offshoot here. We can tell with this one, since it's one standard deviations, we can tell how many percent of the students this was smarter than. You want to see how? Remember when we talked about the bell curve? And we had 1 standard deviation, 2 standard deviations, 3 standard deviations in both directions. What did we say was the percent of people that fall within 1 standard deviation from the mean? How many people are there? You should have on your sheets in front of you. Your graphs that we drew. How many percent of people are within 1 standard deviation from the mean? 68%. No, that's not what you, yeah, then it goes 95, 99.7, right? But let's see if you wrote those down. So if it's 68%, how much percent are on both sides? Yeah, because half of 68 is 34. So half of them below, half of them above. Why do we need to know that? Well, how many percent of the people are to the left of the mean? Which is 50%. And remember, we can't use the words like, because like it means not. It is 50%, or it's not 50%. It's not like 50%. Get away from, in your lexicon, please get away from using the word like so much. Not like say it is or it isn't. Be more precise in your answers. So yes, from the mean, half of the students are below it, half of them are above it. So if it's, remember, this student scored 1 standard deviation above the mean. So we know that's smarter than 50% plus 34%. So it's 84% of the grades are below that one. That's what that means. The reason we can't do the other one because it said 1.5, so it's somewhere over here. And we don't know what that value is. So if a z-score is positive, what does that tell us? To the right, right, of the mean. If the z-score is equal to 0, it is the mean. And if it's less than 0, it's to the left. You want to do another one, or are you okay with it? What's that again? That means that's actually what we want. Because that means it's easy. If your z-score, after everything's said and done, if your z-score is 0, that means you're at the top dead center. You're in the middle of the whole class. 50% smarter than, 50% less than. Or you succeeded 50% of the time or failed 50% of the time. That's much easiest to calculate. Yeah, exactly. So we actually, a lot of students should be lucky to get that high. So that's what it tells us. Is after everything's said and done, once you have the mean and the deviation, you can find exactly where you stand with respect to everybody else. So that's with the standard score. Standard scores deal with the z-score. Next, we should talk about percentiles. What is a percentile? What is a percent? First off, what is a percent? Part over total times 100. Because whatever that is, the reason we multiply by to 100 is to make it a percent. If we didn't have the 100 there, then we just have some decimal. So a percentile is just that. We divide the data set into 100 separate groups, all of the same size. Now, why is it 100? Cent. The word cent. Well, when we the penny, it just got to get discontinued. Why do they call it a cent? How much is this penny worth with respect to a dollar? How many pennies are in a dollar? 100. So if there's 100 pennies equal $1, then it's 1 cent. It's 1/100th. So we will create these percentiles. Where each of these are 1%, all the way to 100%. So far, so good? Now, for example, here's the example I said earlier. If you scored a 58 on your whatever this exam was, the foreign language exam, with respect to everybody else, with respect to listening, your actual score is an 81. Your section 2, your written one, is 76. But what do these numbers mean? What does 81, what does 76 mean? Yeah, but what does it mean? It is part of 100, true, okay, yeah. Oh, it means that your score scored higher than 81% of the other scores. That's what that means in the section one. Your section two, you scored 70 higher than 76% of the other people. That's how you read these percentile scores. When you get your SAT score back, you look at it and you look at your percentile score. That tells you what you're higher than, how many people you're higher than. Percentiles are not the same as percentage. Why not? What does a percentile find? It finds the percent that X is larger than. So if you had a 70 percentile, that means your score is greater than 70% of the other people. That's what it tells you. What is a percentage? That's just part over total. It is a number what a number is. So if you have a 70 percentage, that means you just have 70. That's it. You can't say anything else about anything. Oh, on your sheets, we have the blood pressure example. Systolic blood pressure. How many of y'all been to doctors and they took your blood pressure? When they say two numbers, 80 over 120, what does that mean? Do you ever ask them what that means? You ever know what that means? But no, what does it tell you? Why is it good? It's diastolic versus systolic. The diastolic, the first number, because when they put that thing on the sphygmomanometer, they put that on the cuff on your hand, they pressure it up. What are they doing there? They're crushing your arm so it stops the blood. No, it doesn't affect your height. What it does, it stops the blood down your arm. When they let go of it very slowly, they listen to it. When they start hearing the pulse start coming, it means the blood's flowing now. That's the first number. At what pressure, how much of that pressure is relieved till that blood starts flowing? The bigger that is, the worse off your heart is. In other words, it has a lot of fat in there. Athletes can go down like 50, 60. That's how fast their heart gets back to be normal. That's the reason they can run forever. The second number is when it's open fully and you can't hear the noise anymore. It's not, the heart's not pushing the blood through there. So it means it's fully open. So the closer these are together and the lower they are, that means the more healthy you are. So that's whenever they tell you these things, that's what they're looking at. Hopefully they know this. So with the systolic and diastolic, so we have this information. Let's create a cumulative frequency diagram from this information. So let me write this up down so I could mess it all up. Then we have our frequencies. There are 24 of those, 62 of those, 72 of those, 26, 12, and 4. Because we want is create a cumulative percentage percent diagram. So the first thing we have to do is what? We have our class, we have our frequencies. Well, if we add these up, we'll get 200. Why is that important? That's our N. We need that for our formulas. The next formula we have to create is the cumulative frequency. Remember how to set that one up? Yeah, so what the first number is what? Then it's going to be, right, you add the next, then the next one I get. So 76 plus, or 86 plus 72, 158. 7 plus 8 is 15. 26 plus 58, 184. 184 plus 12 is 196. 196 plus 4 is 200. Remember, these two have to equal. If they don't equal, you did something wrong. Now we have our cumulative percent. Why do they call it a cumulative percent? What's the formula for the cumulative percent? What do you think the formula is? How do we find the percent? Part over total. What's the part? The total is 200. So that's given. What's the part? What part are we looking at? Since it's the cumulative, we have to look at these. So it's the cumulative frequency divided by N. So we have 24 divided by 200. And N times 100, of course, because it's a percent. 24 divided by 200 is 0.12 times 100 makes it 12. So that's 12%. Then 86 divided by 200 is 43%. And keep on going from there. So 158 divided by 200, 0.79 makes it 79%. 92, 98, and 100%. Why is this 100%? 200 divided by 200 is 1 times 100.
So you do like, so let's say,
The cumulative frequency divided by N. So the cumulative percent is the cumulative frequency divided by N times 100. Okay, so what do we do with these numbers here? Now we graph them. And then these are the classes. Yes. All right, we got a couple seconds left. So now, whenever you do these, this is very important. Do I start off with 85 or 89.5? Do I start at 104.5 on my data list? Well, the first one's 89.5. Below that is how many elements? 0. It starts off there. Then I go here to 104.5. Because that's this entire class. So what's the percent of that one? The next one is going to be 119.5. And that one is 43%. And then we'll keep on going. 134. And that one is 79%. Then one, and keep on going from there. So always use the end data. Why? Because they will have everything below that. So when we get to the very last one, which is 179.5, it's going to have 100%. And it's, since it's a frequency distribution, it's always going to be increasing. Okay, we'll finish up chapter 3 next time. All right, everybody, have a great, safe weekend.